Okay, well, remember that our eventual goal is to prove the intermediate value theorem, but it turns out that it's better to prove another theorem first and then see how the intermediate value theorem follows from the first theorem. So what is that theorem? Well, recall that while openness, closedness, and boundedness need not be preserved by continuous functions, compactness is always preserved. Right, we've proven that and shown that the extreme value theorem follows from that fact. Well, we're now going to see that connectedness is another property that is preserved by continuous functions. So more precisely, the theorem says, suppose you have a continuous function f from a to r, then if you have a connected subset E inside your domain A, then f of E has to be connected as well. So let's try and prove this. This one takes a little bit of work. First of all, we're proving an if-then, so we can assume that E is connected. And we're going to use the criterion for connectedness from theorem 3.4.6 to prove that that f of E is connected. Okay, this is a criterion that you proved as one of your homework problems, basically by taking the definition of disconnected and negating it. Okay, so what did that criterion say? Well, basically you're supposed to let B and C be any pair of non-empty disjoint sets. Disjoint means that they don't have any overlap, their intersection is empty, satisfying that f of E is the union of B and C. So basically you're taking f of E and breaking it up into two non-empty pieces. Okay. Now in order to use the criterion, we're going to need to produce a sequence contained in one of these two sets, B and C, that converges to a limit in the other set. Okay, so let's try and draw a picture of what we're dealing with here. You can draw two vertical number lines again for the domain and target. So here's my A, and here's my target R. Okay, and so here's a setup. We have some subset E of A, which I want to just denote like that for now. And if you apply f to everything in E, and there's a function f mapping from left to right, then you get some sort of set over here in R. And we're assuming E is connected. We'd like to prove that f of E is connected. Now to prove f of E is connected, we are going to split it up into two pieces, which I could represent, for example, like this. Maybe this is B and this could be C. Okay, so the union is all of f of E. They're not empty and they're disjoint. They don't have any points in common. Okay. Now we need to generate a sequence in one of these sets whose limit's in the other one. The way to get that sequence is to somehow take these sets B and C and move them back here into the domain. And then we can use the fact that E is connected to find a sequence in one of those preimages, which converges to a limit in the other one. And then we can apply f to that sequence and to the limit to get a sequence and a limit here that do the right thing. Okay. So the first question is, well, what are the sets back in A that correspond to my B and C over here in R? And what we want to do is basically look at all of the points in E which map into B. Okay. So maybe that's Maybe that's these points right here. That's what I'm going to call B prime. And its definition is it's everything in A which maps into B, right, intersected with E, because I don't actually want things outside of E which might happen to map into B. I only want the things in E which do. So that's B prime. And then I do the same thing for C. Okay, so maybe this is C prime, and that's defined to be everything which maps into C and is also contained in the set E. All right, so that'll do it for now for our picture. So let's continue our proof. In order to use the criterion back here for E, we need to check that B prime and C prime are non-empty. And we need to check that they're disjoint, they don't have any overlap. And we need to check that their union is all of E. Okay, so these are all relatively straightforward, but we need to go through them. So first, we check that B prime, which is F inverse of B intersection with E, is non-empty. Okay. Well, we know that B is non-empty, right? So since B is non-empty, well, what does it mean to be non-empty? It means there exists at least one element, let's call it Y, in the set B. Okay. Now notice that the set B is sorry about that, is a subset of f of E, right? So since that's true, and since Y is an element of B, we have that Y is also an element of f of E. Now what does that mean? Well, it means that there exists some x in the original set E such that when I apply f to it, it's equal to Y. Okay. Well then, what do we know about that x? We know that it's in f inverse of B, right? Because when you apply f to it, you get Y, which is in B. And it's in E, as stated in the previous sentence. Okay. So there we found an element in f inverse of B intersect E. So B prime is non-empty. And we can just say that similarly, C prime is also non-empty. Okay. So we have B prime and C prime non-empty. How about next we show that the intersection of these two sets is empty, so that they're disjoint. So for that we have, let's see here, B prime intersect C prime is by definition f inverse of B intersect E intersect f inverse of C intersect E. And the parentheses don't matter so much here because they just have the intersection of four sets. So you can drop those. And in addition, intersecting with E twice, the second one doesn't really do anything. So this simplifies a bit to f inverse of B intersect f inverse of C intersect E. Okay. Now, there's a property that says that F inverse of B intersect F inverse of C is equal to F inverse of B intersect C, right? Because if an element maps into B and it maps into C, then its image must be in both B and C. So we have that intersection. And then B intersect C, well, remember those are assumed to be disjoint sets, so their intersection is the empty set. So this is F inverse of the empty set intersect E, and F inverse of the empty set is just the set of all things which map into the empty set, and that's nothing, right? So this is the empty set intersect E, and the empty set intersect with anything is the empty set. So we're good. We get that B prime and C prime are disjoint. Okay. Well, next, let's show that B prime union C prime is equal to the entire set E. Okay, so we have B prime union C prime is, by definition, F inverse of B intersect E union F inverse of C intersect D. And now we want to use the fact that the intersection distributes over the union. So we can sort of factor the E out of this to end up with F inverse of B union F inverse of C, and then take that whole thing and intersect with E. Okay. So you can think about why that works. It's not too hard to make some sense out of that. All right. The next step is just like before. The union of F inverse of B and F inverse of C is the same thing as F inverse of B union C, because to be in either of these sets, F of U has to either be an element of B or an element of C. Okay. So we have that intersect E. And then remember, we assumed that B union C was the entire set F of E. And we're almost there. This here means the set of all elements in A which map into F of E. Okay? And everything in E certainly satisfies that requirement. So this set here is a subset, contains the set E, and so when you intersect it with E, you just get E itself. So as desired, the union of B prime and C prime is equal to E. Okay, so we know that B prime, C prime are non-empty, they're disjoint, and their union is E. Therefore, we can call upon this criterion. We can say, since by assumption E is connected, theorem 3.4.6 implies that there exists some sequence x sub n contained in one of B prime or C prime with limit of x sub n equal to some number x contained in the other. Okay, so the sequence is in B prime or C prime, and x is in the other one. All right. Well, now we want to transfer that information forward using the function f. So because f is continuous, in particular at this limit x. We know by the sequential criterion for continuity that limit of f of x sub n is equal to f of x. And so it follows that the sequence of the f of x sub n's is a convergent sequence. And since the sequence x sub n was contained in one of b prime or c prime, we know that when we apply f to it, the resulting sequence is contained in either b or c, while the limit f of x, well, that was contained in the other one of b prime or c prime. X was, so f of x is contained in the other of b or c. All right. So using the theorem 3.4.6, this time in the other direction, right, we get that f of e is connected as desired. Okay. So the big outline is we took a decomposition of f of e, pulled it back into a decomposition of b prime and c prime, of e into b prime and c prime, and then we used this criterion for connectedness to get a nice sequence and limit back here. Push them forward again with f to get a nice sequence over the sequence in b or c and the limit in the other one. And then we used the same criterion backwards to get that implies that f of e itself is connected. And that finishes the proof.